Hello and welcome back to the Solving Exponential Equations lesson. This time we'll take a look at a new group of exponential equations. So let's consider the equation 16 to the power of x minus 5 times 4 to the power of x plus 4 equals 0. What makes this equation different is the fact that it contains 1, 2, 3 terms. The first term is in exponential form. The second term is a product of a constant with an exponential term. And the last one is a constant. When we deal with such equations, we focus on the exponential terms. And we try to make them with the same base. In our case, we have the bases 16 and 4. And we'll change the base of 16 to a base of 4. Always change the bigger numbers into smaller, make them smaller. And then we have minus 5 times 4 to the power of x plus 4 equals 0. We'll apply the power rule in here. We have 4 to the power 2 to the power of x is 4 to the power of 2x. And then minus 5 times 4 to the power of x plus 4 equals 0. Now remember that in these equations, the terms are separated by a minus and a plus. So there is no way we can combine the terms because exponential numbers cannot be added to each other by any exponent laws. And here I'm going to show you a neat trick. So notice how here we have 4 to the power of 2x. Instead of writing as 4 to the 2x, I will rewrite it as 4 to the power of x to the power of 2. So see? I haven't done anything wrong because x times 2 is still 2x. And then minus 5 times 4 to the power of x plus 4 equals 0. And next, I will take 4 to the power of x and replace it by what I call a helping variable a. So 4 to the power of x squared now changes or turns into a squared minus 5. 4 to the power of x is a and then plus 4. So do you see the trick now? So we have created a quadratic equation. Do we know how to solve this? Oh yes, we can factor. Each factor will be in binomial form starting with a. We need to find two numbers that multiply to 4 and add to negative 5. Negative 1 and negative 4 will do the work. And now we can solve for a. We'll say either a minus 1 is 0 or a minus 4 is 0, which tells us that a is 1 or 4. And now it's time to pause for a second and think, wait a second, so I solved for a, but that's not what I was looking for. I need to know what x is. Well, now that we know the values of a, we can make them equal to 4 to the power of x. Because it is no secret that 4 to the x and a are the same thing. So we'll say 4 to the x equals 1. Wait a second, how do I solve this? Well, I need to make both sides of the equation into exponentials or exponential terms with base 4. So I'm going to write the 4 in here and I have to think what power do I have to place in here for the exponent so that 4 to that power would equal 1. So we'll say 4 to the 0 equals 1. Now we have two exponential terms in each side, and we'll say that since the exponential numbers are equal and their bases are the same, it means the exponents must be the same. So x equals 0 will be one of the solutions. And next, we'll do the same thing for the next solution, a equals 4, which means that 4 to the power of x equals 4. Compare the powers, and the second solution will be x equals 1. Now, it's time for you to try an example on your own. So you can pause the video and try the next example. If if you'd like to listen, of course, I'll continue solving it. So let's take a look at this equation. We have 6 to the power of x, one term, plus 36 times 6 to the power negative x, or another exponential term, equals 37, a constant term. So this looks a lot like the previous equation, but with one difference. So we have a negative power. We don't want to work with negative powers. Whenever we see them in equations, we change them into positive. So 36 over 6 to the power of x equals 37. So now, as you see, we have various terms here, some in rational form and some regular terms, exponential term, rational, and a constant. So we want to eliminate the denominator, and we can eliminate the denominator if we multiplied each term in the equation by the lowest common denominator. So we're multiplying both left and right side of this equation by 6 to the power of x. We haven't broken any rules, not yet. So we have 6 to the power of x times 6 to the power of x. And then plus. Now remember that we have 6 to the power of x times 36 over 6 to the power of x equals 37 times 6 to the power of x. Look at that. So this too will simplify. 6 to the x times 6 to the x will be 6 to the x plus x 2x. 37 times 6 to the power of x can come to the left side. And then plus 36 will be the constant term. And what I'm going to do is the little trick, 6 to the x squared minus 37 times 6 to the x. We don't have to make it this obvious. It's just that we're having fun learning this for now. Equals 0. Now it's time to substitute 6 to the x by a. You can use any letter of your choice, by the way. A is my favorite letter. So we have a squared minus 37a plus 36 equals nothing. And let's solve this beautiful quadratic equation. Factor. A is the first term. Negative 36 and negative 1 will fit perfectly well, nicely in here. And we'll have a equals 36 or a equals 1. Bring back 6 to the power of x. Which is 6 to the x equals 6 squared. That will give us the first solution, x equals 2. Go to the other solution, a equals 1. We'll say 6 to the x is 1. Or 6 to the x equals 6 to the power of 0. So x equals 0 will be the second solution. So this was the sixth example of the lesson, and there are quite a few questions here that I suggest you practice for homework. And as a matter of fact, I want to actually browse through and I want to do a couple of questions from your homework that are slightly different than the examples that we did in this lesson. I'm pretty sure you can figure them out yourself, but why not take up just a few of them? We have 2 to the power of x plus 2 minus 2 to the power x equals 24. So notice that here we have three terms, exponential, exponential, and a constant. Now the two exponential terms cannot be subtracted the way they are because there is no law that connects them. On the other hand, if we look at this term in here, we cannot use the same strategy as before by bringing it to the power of 2. So we will have to think a little bit differently. So the sign you see between the terms in the exponent is plus, which means that this exponential number has probably come from the multiplication of 2 to the x with 2 to the power of 2. So we'll write it down, and then we have minus 2 to the x equals 24. So 2 squared equals 4. So we have 2 to the x times 4 minus 2 to the power x equals 24. We'll bring the coefficient 4 first to the front, and then we have 4 2 to the x minus, 1 2 to the x in here equals 24. So if you have 4 2 to the x and you subtract 1 2 to the x, then we're left with 3 2 to the x. I hope you can see this, right? So this can be seen as a single variable, sort of to speak. Let me make this green so it's not confusing with this other pink. There is no connection. Okay, so we have 4 of them minus 2 of them, 3 2 to the x. And isolate 2 to the x from 3 by dividing both sides by 3. So 24 over 3 is 8. Look at this. This is a beautiful number. So that's 2 to the power of 3. X equals 3. Voila. So what did we learn from this example? Well, sometimes we have to use the power law in order to simplify the terms or combine them. Sometimes we have to use the product law. Depends on what we are given in the equation. So I'm going to take a look at another example. It is similar to the examples that we did in the previous lesson when we talked about logarithmic equations. But I think that is a good idea that we practice this one more time together. So here we go. We have 2 to the x equals 3 to the power of x plus 1. This is an exponential equation with different bases. Not only different bases, but bases that cannot be expressed in terms of a common base. And I'll make a note in here. So bases can't be converted to a common base. So if you remember from the previous lesson, when that happened, we took the logarithm of both sides. So we say logarithm of 2 to the power of x equals the logarithm of 3 to the power of x plus 1. A log with base 10 is fine. Now remember that for the powers, we can apply the logarithmic laws. So the powers can come to the front as coefficients. We have log of 2 equals x plus 1 log of 3. Remember to keep this exponent, when you bring it to the front of the log, in brackets because it's in binomial form and it will multiply the log. So we have x log 2, and I would keep the x in front of log, and that's because if we tried otherwise, it is very easy to confuse the x and think that, oh, x must be inside the log, right? So if you write it this way. And then we'll expand this. We have x log 3 plus 1 log 3, simply log 3. So the x terms appear in two the x variable appears in two terms. So we have x log 2 minus x log 3 equals log 3. So in order to isolate x from these funny looking coefficients, we'll have to factor it. We have log 2 minus log 3 equals log 3. So divide both sides of the equation by log 2 minus log 3. Oops. So now x is all isolated, all by itself, and it equals log 3. And notice how here in the denominator we have log 2 minus log 3, which means that we can combine these two terms using the quotient law for logarithmic numbers. So this will be log of 2 divided by 3. So this would be the exact answer. X equals log of 3 divided by log of 2 over 3. Now we're going to take a look at one last example from your homework. Here we go. 27 times 3 to the power of x to the power of x equals 27 to the power of x times 3 to the power 0.25. Notice that we have a group of terms in each side of the equation. Examine the basis. So we have the product of 27, which can be an exponential number, 27 power 1. It's multiplying 3 to the power of x. And again, we have 27 and 3. We can convert 27 into 3 to the power of 3, multiplying 3 to the power of x. And remember that we still have the power of x outside the big brackets. Equals 27 to the power x is 3 to the 3 to the power of x times 3 to the power of 0.25. Now always do the brackets first. So we have 3 to the power of 3 plus x, all this to the power of x, equals 3 to the power of 3x, so we have to apply the exponent, so power law, times 3 to the power of 0.25. One last step. We have 3 to the power of, now we're multiplying x by every term in the exponent, which is in binomial form. So that would give 3x plus x squared equals 3 to the power of 3x plus 0.25. So notice how we have created an equation where we have a single exponential term in each side. The bases are equal, which means that the exponents must be the same. So we have 3x plus x squared equals 3x plus 0.25. Oh, this is kind of interesting. So the 3x's will simplify, and x squared will be 0.25, or should we say x squared equals 1 over 4, 1/4? And from here we can find the value of x as the square root of 1 over 4. Don't forget, plus or minus. So therefore, we'll say that x equals either 1 over 2 or negative 1 over 2. And voila! I think that this was plenty of examples for exponential equations. And I hope you enjoyed learning more about exponential equations. And I thank you again for choosing to listening to my lessons. Leave me a comment if you have any questions. I'll try to answer as quickly as I can. And subscribe and give it a like if you like the lesson.